Okay, because we have just 1 hour remaining, shall we?
Yes.
I normally come with my duster. I forgot the hanky the other time.
Give him take paper for you. Come and take paper.
I don't want to use the paper.
That is my paper. So you think every day. Wait, I have that Hey,
But you come and start tearing your video.
Okay, you don't want me to tear my paper. What is this one? Your entrance.
Alright. We are supposed to be doing wait for another word. We are tired. Just push. Do a push.
Yes.
Alright, see please now we are supposed to solve calculations from our notebook. But because we have limited time, I just want us to focus on 3 things. And that is angles found on an inclined plane. Yes. Why am I doing this? So that when I start the calculation now, I won't have to be explaining it again. Yes. I'll be sure that I've thought that one. This thing is an inclined plane, is it not?
Yes.
If, for example, somebody, this is the wall, and somebody places that here, and the person is climbing up, maybe that person wants to climb up. Are you noticing that what this ladder creates with this wall is like an inclined plane? Is it not true? So it's important to understand that inclined plane principle very well, so that we will not use it to solve questions on equilibrium. Because under that equilibrium question, you will definitely come across where they will be telling us to calculate angles found by a man climbing ladder, or by a ladder that is placed that somebody falls down. They ask us at what point will the person fall down. Definitely, you know that if I carry this ladder and I place it very close, let's say I have this ladder now, I have the wall, and I come and put this ladder somewhere like this.
This camera is not.
Like very close.
Stand up and check. Make sure it's
Let's say you come and put it somewhere like this, very close.
Stand up and check it now.
So that the angle is really very stable. Should you know there's a point you get to that, you and this ladder will fall like this. Should you know? So that is what physics asks us. I remember that we are studying the last part of any part of equilibrium. Static equilibrium. And when we say static, it simply means it's not moving. So if you know that, and in fact, even the concept of equilibrium means that anytime I'm dealing with equilibrium, there is no acceleration. Acceleration is zero. What do you know? Yeah, that is why we say there is no net force. So with that in mind, let's now look at this. Let's understand the concept of things that happen here. So that in our next class, when I start to solve all the questions that relate to this. Now please, let's take it that this is my wall. And now let's take it that this is the ladder. Somebody wants to ask me, so I draw the ladder now? No. I'm not drawing the ladder because that ladder is not what I'm looking at. What I'm looking at is what it creates with the wall. So the question will always focus on, I'm teaching you because I know what you're expected to do. So I'm not going to have to start drawing the ladder vertically. So what are the forces acting on this wall and this ladder? That's what I'm looking for. First of all, what are the forces that will be acting here? If they say a man is climbing this ladder, let's say this man is somewhere here. Okay, let's say this man, this is this man. Manage it. So let's say this is 6.
It's okay.
Yes. So the next answer I want you to see what I'm doing. So if they ask me that this is a man, they tell me what are the forces on this ladder and what are the forces on the wall. Those are the two kind of questions to expect. So first of all, I need to say that there is a force acting here. Is it not true? Because this ladder is pressed against this wall. There will be force on that wall. And as it's pressing the wall, the force will be giving its own force back to it, which is that principle of Isaac Newton, third law. So every action, as you are standing, there is force acting on you that was. Is it not true? If you get to a place where there is no force acting on you, you see that your leg will be like this. Yes. So that is the first force I need to know for this. So I can call it force of the wall. Please, whatever I teach you here, your own is to understand it, learn it, memorize it. No matter how this question comes, no matter even if it's 100 times, long as it's the question of a linear ladder, or linear ladder of the wall, it's the same concept. Alright, now the next thing is, the ladder itself, as I place this ladder on the ground, notice that the ladder on this ground, as it's on the ground, there will be a force acting on this ladder upwards. Just like my own self, there's a force acting on me, my normal force. So there will be force on this. But let me do it here so you know. Okay, let me put it close because I'm so beautiful. So let's say, let me go on this ladder well so you see. In that case, let me take this back. Yes, the side of the ladder should be like a rod. So this should be the force acting on this way, force on the wall. Then, as I place this ladder, there will be a part of it standing this way, but there's a force this way. And that force is equal to whatever. So I have force of the ground, which you can call any, but I just use to represent it. So then, notice that, hello, if this ground, if this floor is not level enough, if this floor happens not to be level enough, should you know that the next thing that will happen is this ladder will slide. Is it not true? Okay. So, a situation where this thing is standing and this man is able to climb it successfully. The man is able to climb it successfully. It simply means that there is friction on this opposing motion. So that means there is friction on this going this way. Because if there is no friction this way, this thing is simply so let me put my friction here, FF of friction. So Shebi, you see, when it has to do with the wall, the ground, and the ladder, these are the forces. But let's go to the ladder itself. Shebi, you know that there will be weight on this ladder. This no weight, right? Shebi, you not have weight. Do you have weight? And you see that?
Yes.
Now, if that is true, what did I tell you about center of gravity? Weight is the center of gravity. Are you aware?
Yes.
Yes, because you now know that it's going to be the center as energy. If that is the case, where will the weight of this ladder be acting? Downwards towards the center. Downwards. Is it not true?
Yes.
So that means, let's say this is the center. Let's say this is the point of the center. Will it be going this way? Or this way? 90 degrees downwards, Shebi?
Yes.
Thank God. Please, if you are just coming, be taking note of this thing. Somebody might want to tell you because it's facing like this, the gravity will be facing like this. It's not possible. So downwards, vertical. Okay? So if I know that for the ladder, so let me say this is weight of the ladder. What about the man? Should you know that this man is exerting force on this ladder? Is it not true? Yes. And as he's exerting force on the ladder, because he's going vertical, it will now be weight. You know that force is the same as weight. So that means that there will be weight on this as well, weight of the man. So let's say this is where the man is standing. Assuming he's standing at this center, that means that the weight that will be on this center is just the weight of the man. So the situation where he's standing here, that means this is the weight of the man, WM, weight of the man. Please, you're writing your own, if you write all these things, so you can go to some place you're not doing. When I'm doing these things, so that when I'm solving tomorrow, I don't have to be doing all these things today. So go to your book, solve and write where FW stands for force on the wall or the reaction of the wall. Where FD stands for reaction of the ground. So in fact, I don't want you to be using F, using R, reaction of the ground. We say N. So normal reaction of the wall, normal reaction of the ground. Then this one stands for friction. Preventing it from sliding. Why this one stands for weight of the ladder? Acting towards the center, downwards. Why this one stands for weight of the man, acting downwards. Alright. Very important to know all these things. This is the reason why you are a science student. When you are a science student, is that by the time you finish doing this, you go and memorize it. It becomes part of you. That, if the kind of question come out again, nobody will see it as a problem. You know, see it as a problem. I said, where end of this stands for normal reaction of the wall. Notice that the ladder is giving it the reaction or the force. Him is giving normal reaction, giving it back. Then I said, where this one end stands for normal reaction of the ground as the ladder is placed downwards. Remember that this force is actually here. I put it here so I have to use drawing. So if you want, you can draw your own here so that when you are ready, you'll be able to see it. So, normal reaction of the ground. Then, I said that this one stands for frictional force. And remember that the kind of frictional force that is acting is static friction. Maybe you know. When the body is not moving, the type of friction experienced there is static friction. So, preventing it from sliding, because if there is no static friction, it will just do here. The man will go home. Yes. So then the weight of the ladder itself will be acting vertically downwards. Please always see it, no matter how that thing is placed. Weight always acts 90 degrees downwards. Then weight of the man downwards. Now that you've done that, it is different from when we talk about torque. Should you remember what I said torque is? Torque is what? Define torque. Product of force and perpendicular distance. And that is what we are talking about, moment of the force at a point. Is it not true? What's the torque of a couple? When you are talking about a couple, two forces of the same magnitude or opposite direction. When you are talking about the torque of a couple now becomes product of force and perpendicular radius for one force. Product of force and perpendicular radius for another force. That means two of them now becomes 2F. Very good. Alright, so now that I know this, if I tell you to find me the equilibrium of force here, equilibrium of force here, is different from when I tell you to find me any of this. Maybe I tell you find me NW, or find me WF, or find me WF, or I tell you find me NG, I tell you find me this one. It is different from when I tell you what is the equilibrium of force here. Because you remember that equilibrium of force, whenever they ask you that question, you are simply going to be thinking of three things. Is it not true? I gave you the three rules. Here you will be checking for forward, upward force, checking for downward force, that there must be equal. Then you will be checking for clockwise moment and anti-clockwise moment, there must be equal. Is it not true? Then you will be checking for torque. Is it not true? Whether the clockwise torque and the anti-clockwise torque, if they are equal. But when I tell you find any of the things here, instead of stressing yourself to be looking for these three things, all you can just do is to use our shortcut, which is torque. Do you still remember? You make torque, make one the fulcrum, such that you're not calculating anything for that one. Direct all the forces to that one. Or you make this one the fulcrum, you're not calculating anything for this, because because the fulcrum is not, you're not considering it to be rotating. Then direct all the forces to this one. If they ask you for any of this, use our shortcut, that's what I'm saying. But if they ask you for the equilibrium, you will always apply the three rules. Alright, so let's try to apply that three rules here and see something. So starting first, for equilibrium, that is upward force. Number one. Upward force from the upward to downward force. Upward force from the upward to downward force. Please, how you learn this thing is make room in your mind that once you learn it, the way I'm teaching you now, your own is to research, read, and add to it. But you are not taking it and maybe after seeing it this way, you go somewhere and see something different. No, that's why you are here. So as I'm teaching you, have it in mind, at the center of your mind, that whenever you have to do it, a word, a living ladder question, that the person who is leading you here and the person who is leading you. In fact, anything else will be wrong. Anything that will be wrong. If they ask you what is the equilibrium of forces, think of three things that I just mentioned. But they ask you to find any of the forces here. The easiest way not to stress yourself is simply make one fulcrum direct all the forces, or make the other focus. Or if possible, if they ask you to find this, or find this, you can actually direct the forces to 3 places. Either I make this 4 direct all the forces here. I make this 4 direct all the forces here. Or I make this one the 4 the center forces, say to the center force, the 4 direct this to the center. So there are 3 ways. And as we are solving questions, you will see it playing out. So upward force equals to downward force. So let's check. Our upward force is here. Let's say this is my y, this is my negative y. See that? But what are my upward forces? Let's check for the upward forces. What are the forces going upward in this case? Energy. Energy, should we?
Yes.
Okay, let me clean. Okay, let's use this with energy. Now I guys have got the air. What about any other upward force? But what about downward force?
They have the weight of the ladder and the weight of the boy. The weight of the ladder.
That is weight of the man and weight of the boss, weight of the ladder. I said it. I'm putting plus because they're in the same direction. So which means that if you check it, actually upward force now becomes normal reaction of the ground minus weight of the man plus weight of the ladder. And notice something. If I am putting this thing, if I'm putting this thing in a way that it goes in to be equal to 0, it simply means that what I have here should be this way. Yes. So that minus is actually, the minus is actually for the 2 of them because they're in downward direction. Is it not good? Do you remember that y down here is minus? So let's say everything here is y, then it's minus. So that by the time I push it to the other side, you see that this minus will be, but it turns positive. Yes, very important. That is why normally, that time we did everything here, we normally do minus, because if we cross over. So this now becomes ng is equals to, that is here, since it's having minus. First of all, this is the sentence that says ng minus wm. Minus wm. You see now equals to 0, which is the sentence that says ng minus, but since they are not the same, shall we? Because, but see something, this is weight of the man, which is mg of the man. Let me change it this way, mg of the man, and this is weight of the ladder, mg of the ladder. Are you confused?
Yes. It's okay, it's service. Yes.
It's too early for anybody to. What's confusion? What's your question now? One person from there. Sir, what's this one? So, for the sake of peace, up to this point, you understand why we stress this, Chevy? Yes. That is why. So that ng is simply equals to Wm plus Wn. Another way to do it is simple. By the time you've got this now, you can say that upward force must be equal to downward force. You just say ng for upward equals to downward, which is Wm plus Wn. So it's the same thing. You need to know that. Now the second rule, if I'm to get this, the second rule that will always be there is a must for equilibrium to be achieved here. If you solve using this for equilibrium, you must still go and do the second rule then before the third rule. So the second rule is simply sum of clockwise moments must be equal to sum of anti-clockwise moments, which is the same thing as saying sum of parallel forces must be equal. Sum of parallel forces must be equal. So number 2. So sum of parallel forces are the same clockwise and clockwise moments. So that this now becomes, if I have this now to the x, and I have this to the minus x, okay? I want us to check something. Which one, if you check this now, what are the forces in the negative x-axis and what are the forces in the positive x-axis here?
Negative is frictional force.
And you guys will come down to the
Negative is frictional force.
Okay, I'll see that this is going this way, Shani. But let me just put it for this side. So I'm saying frictional force, this side. Then, is there any other thing going this way?
no.
Okay, then, just this one now. Going this way. End of it. Is it that way? So if I know that, which means that this now becomes the sentence I'm saying, if they are going to be equal, I can say that this is the sentence I'm saying, minus then plus NW. And it doesn't follow the rule because X is constant. So I have NW, that is normal reaction of the word minus frictional force is equal to what? Do you know that this thing is the same thing as saying upward force minus downward force equals to 0? Do you still remember when we normally do that? Do you still remember? Because if this thing happens to be upward force or the forward force, this becomes forward force and this one becomes the backward force. Is it not true? Now why are we putting 0? It's the same thing as equals to MA because these are the forces here. Remember I told you that force is equals to MA only when you have one force. In our dynamics class, we still do it because we started from the beginning. But the reason why everything here is becoming 0 is because in equilibrium, acceleration is 0. And 0 times it becomes 0. That is why you're seeing us pointing everything to the equals to 0. So if that be the case, I have that this is equals to 0. Which means that this plus equals to 0, this plus normal reaction of the wall is equals to frictional force. Very important. Noting all these things. Once you start solving calculation, if you're able to memorize it, you see that as we start solving calculation, the questions, no matter how the question is, it will just be playing out on this own.
Amen.
Yes, amen. Alright. So that means for the third one, which is the top, I don't know if I can put it that side.
Pulling it.
Okay, so the third one is the sum of torque. Clockwise, must be equal to clockwise torque. So which means that you can say that some of the torques must be equal to 0. It's the same thing as saying clockwise torque is equal to anti-clockwise torque. That's the same thing. Now, what is torque? But remember that torque is simply force times perpendicular distance. Correct. Now, whenever you want to do torque, please, I want you to always look at your diagram very well. Every diagram that involves linear ladder problem is a topic on its own, or it still falls under individual. Now, whenever you are doing this, I want you to be checking your unknowns. Let's look at this. Notice that nothing here was given to us. They did not give us any value for n of this. They did not give us any value for everything we have here. So we are taking it that everything here is unknown. Now let's check. Here, how many unknowns do I have? Up here. How many? 1. Shebi? What about here? Guys, Shebi, you know that this one is unknown at the center. Is it not true? What about this one? It's not at the center, I hope you know. It's close to the center. We can say it's 2/3 or 3/3, but it's not at the center. Look at it very well. This is our center now. Is it not true? That means this one has its own distance. Like if you are considering from this end, let's say you have this to be our ladder. If you are considering from this end to this end to be from this point to this, that means that this one will be from this end to this end. Is it not true? Why this particular one will be like from this end to this end? So they are not at the same position. So at different positions, there are different things. So you can clearly see that what you have here is one unknown. What you have here is one unknown. What you have here is one unknown. But look right here. Look right here. How many unknowns do you have? 2 unknowns. There is a force acting on this upwards because of the fact that this ladder is touching the ground. And then there is a force also acting on this particular ground this way because this ladder is touching the ground, preventing it from sliding. I said it. Yes. So whenever you are doing linear ladder problem, when you are finding your top, can you hear me? Always make the point of that your fulcrum. Remember what I taught you, that you always point your force to one side, then point your force to the other side, all your forces to the other side, in order to achieve equilibrium using torque. Which means that anytime you are finding torque, in this case, always make that point that has two unknowns, your fulcrum. So that means that as I'm doing this now, I will take it that this becomes my fulcrum or my pivots. This becomes my pivots. This one becomes my pivot. So which means that I'm pointing all the forces here down to this point. Now somebody wants to ask me, why did you make it your pivot? Because I cannot be looking for two things at the same time. So if I'm successful in using the ones I have to find it, I can now say, okay, the friction given to me here, did they give me the coefficient of starting friction? That is that mu. Did they tell me, say, you know that friction, first of all, is equals to coefficient of starting friction times scalar reaction. Yes. So when I'm able to find all these forces, I can now be checking, was anything like this given to me? In a situation where it's not given to me, what about this one? Have I been able to solve something for this? That's the reason why we said always point it down here, so that those two unknowns will give you issue. So as we start solving the questions, you will see, but even as we are doing this, you will see it playing out. So that is why I said always make it your fulcrum. So with that said, let's try to point knowing what we know. But look at this very well. If this happens to be my ladder, and I know that torque is equal to force times distance. And I told you that you should always consider the force when it has to do with a torque to be at 90 degrees. Do you still remember? Why your horizontal axis is your x axis. That is your horizontal axis is your distance. Hope you still remember. Yeah. Now let's check something. If I have a force this way for WL, for example, let's start with WL. Let's start with WL. Remember, please notice something. Remember, this is our ladder. This is our ladder. This ladder, as this man is standing on this ladder, his weight is acting downwards this way. Now I want to ask you, the force that is acting on this man, as a component to this ladder, to this particular ladder, is it 90 degrees at this point?
Of the man. Yes.
It's standing in an inclined way.
Yes, it is.
I have this. Watch, pay attention. This thing looks more like it. See the only part I want your eye to be on. This is your wall. I see.
Yes.
Now that you are looking at this thing now, please, even if you are there, try and be looking at something. Now that you are looking at it, I want you to be checking something. You must be looking at something. Just be paying attention to that part. Maybe you see people that will come to this hall and forget their material. Okay, for this school, people are wasting their parents' money, but they don't know. Don't worry. Alright, now please, as we are watching this now, let's check something. If something happens let's say a man happens to stand here, or let's say we are just considering the weight of this, and we said that the weight of it will be acting straight down this way. As it's acting straight down to this particular ladder, this force that is acting this way, is it at 90 degrees? Yes. If you say it's 90 degrees, let's check something. If this ladder happens to be straight, this way, if this ladder happens to be straight, this is this x-axis, is it not? Chevy? Yes. Why this one is this vertical axis, right? It cannot be straight. This force cannot be straight on this ladder. That is the component, because of the fact that notice that as you bend it, you've kept this at an angle, this particular one. This particular axis that is supposed to complete with this particular one to give you 90 degrees. You see now this angle, these two angles on this ladder that are supposed to give you 90 degrees. Chevy? Yes. Those are the two that are supposed to give you 90 degrees. Now notice that as you bend it, notice that what you have for the ladder is this way. This way, everything. Is it not true? So this particular this particular weight you are seeing here is acting downwards 90 degrees. But for this ladder, this particular ladder, this force component here is not at 90 degrees. Because if you want to get it 90 degrees, you have to be pointing the force in such a way that by the time you place the ladder straight, you are seeing that this particular 2 points gives you that 90 degrees. And notice that if I have this thing now, the way this one is going, let's say I come here and check, let's say this thing and I come and put it here, this is direct this way. Then notice that there's this thing this way. Are you not seeing that it's at an angle and it's not 90 degrees? Should we see it? So for this now, for this to actually be at 90 degrees, this more now has to be this way. So that is why we have what we have. Whenever we get this, if we are getting the torque, since torque, please pay attention. Since torque is simply force acting on an object and perpendicular distance, it must be 90 degrees. So this particular force is 90 degrees through when the force is going through. Yes. So it is simply, watch now, I've pointed this force to be parallel to this because this is the ladder. So this force is not parallel to this. And this force is also parallel to this. So according to this ladder, its force components that must be at 90 degrees is when you have this force to be parallel to this and to be parallel to this. Because this one already is the particle that is at an angle. So once you have this, you can now see that clearly. Once you have this way and this way, that gives you 90 degrees. But assuming I use this one now, notice that what I have here, and this one now, this thing is not 90 degrees. Are you seeing it? No. That is the first point you must note. So if that be the case, I will go on and find all the 90 degrees or the first components of the forces here before start doing torque. It is not hard. You are just seeing it that way because it's your first time. So this is the concept you must use. How do you make it in such a way that all the forces there report to be at 90 degrees? So notice that, let's check for NW. If I bring out this ladder, and I already have something moving this way. Watch. Moving this way. If I say that this thing is 90 degrees, let's check the ladder. You see that now because this thing and this thing is not 90 degrees. It's not because this and this, it's not 90 degrees. Is it not true? Yes. So what I need to do is to check, how do I make this particular line now to have a 90 degrees? Now notice that there's a force, there's a line of action here. Now if I point this particular line to be parallel to this, notice that that thing is at, because then I have, notice, this line, how did I get this line? I made sure that it's parallel to this. Can even make it, let's say I go this way. So, how you get this is simply using corresponding angle method. We are trying to make sure that whatever we have here and whatever we have should resolve to us getting 90 degrees. But if this method is hard, we now use a practical or a simpler approach. Is this one hard?
Yes.
But you are understanding it?
No.
Hey! Zachariah, see. Pay attention now. Since that method did not work for you, but that's the same, like more like, should I say, you just do it about one, you just get your answer. But let's now use a method that you must understand, which is a simpler method. Watch, please pay attention. If I have my force acting 90 degrees to this, is it not true? That means everywhere on this I have a parallel 90 degrees. Is it not true? Hope you agree. Even here I have 90 degrees as well. Hope you know. Since there's 90 degrees lighting this way now, that is according to the weight, not really according to the ladder. So using that now, you see that if I point this ladder now, and then that weight downwards, then notice that there will be an angle given to me here. Let's say this is my theta. Is it not true? So if you check it very well, you see that this time becomes your theta. Is it not true? So we've been able to carry that force, no matter where you see the force. Remember I told you that time we did vector, parallel forces are equal. So if I have that force acting downwards this way, it simply means that I can come and carry it downwards this way. which is the same thing as saying if I have this to be my ladder and I have a force going this way, it is the same thing as saying let me come and carry this force to this point, or I can even carry this force to this point. They are going to be equal. It's the same force. Parallel lines are equal. So if that be the case, I can use that same thing to get the angle here, then get the components. So what I will do in this case is to say, what angle is here? This is theta. Now remember that away from the angle we use what? Towards the angle we use what? Cos. Is it true? Yes. Now remember that talks about 90 degrees. Is it not true? First and perpendicular distance. Now this thing that I have here from this point to this point is not 90 degrees, it's more than 90 degrees. Shebi, how do I make this now to become 90 degrees? Remember that this one is already at y-axis, Shebi? So if I'm carrying this particular force here to this x-axis so that everything here gives me 90 degrees, what does it mean? Am I going towards the angle or away from the angle? And when you are going towards the angle, you use what? That means that any force on an inclined plane that is acting downwards, vertical, is going to be cos. Because if I carry this thing now to this place, notice that I've gone towards the angle, which means that y here, guys, the force here, the torque here, is going to be simply cos. See that? And remember something. Remember that we have this side to be our mg. Is it not true? This side is our mg now. Now, if I'm carrying this now, this is actually my ladder. So if I'm going this way, to close that angle so that I look up. You see that I'm now having my cos theta to use. So I've been able to get that angle. So if this is 90 degrees, that means that the angle that I'm using, resulting into, is going to be really 90 degrees. So that is another approach to get it. That is the second approach, which is simpler. If I have my end of view again, please, why I'm doing this, so you pay attention and learn this. When we start solving questions, I will be repeating these things. If I have my end of view to be this way, my ladder, sorry, to be this way, and I have my end of view to it horizontally, the force here will be parallel. Notice that it's acting at this extreme end. It will be parallel to the force that is here. Yes. So if I know that, notice that the ladder itself has an angle to it. So that is the same thing I said, if I bring it out and point this way, there's an angle here. Now I will ask myself, if this is angle theta, what do I need to do now? There's already an angle, NW here now. What we are trying to do is to say, resolve that ladder in such a way that it maintains 90 degrees, because that's what torque is. Torque simply means, in this case that I'm having this, how do I make this thing? If it happens to rotate, how do I make it to? Remember what we first said, a moment is turning effects of force. We then said a moment at a point is turning effects at force at perpendicular distance. So how do I make this ladder now to rotate at 90 degrees? So if I'm pulling this ladder now to 90 degrees, you see that I will be going away from the angle. You see that? I'll be opening this angle. So the angle I'm using here is what? Sine theta. Now, another way now, the last method to know it, instead of you suffering yourself to do this, is simple. Once a force is on an inclined plane, take anything that has to do with y-axis to be equal to cos theta, and everything that has to do with x-axis to be equal to sine theta. So this one that I'm giving you is a rounded up summary of what we're trying to derive here. So anytime you are dealing with, normally we know that normally when I have a body on this quadrant, we normally say that each one should be considered at 90 degrees. This thing, remember our class. And now when we consider each one to be at 90 degrees, you must pay total attention. If you are paying this attention half and half, you are somewhere now that you are no longer with us. Let me tell you, whether you believe me or not, physics, chemistry, and mathematics, they are not mates. Because there's a part you now get to in physics, you now start to see that physics requires complexities. You really need to be paying attention. Small thing that you know like this, you see it in another place, you think it's a different formula. No, it's just an extension of that formula that you know. So you need to pay attention. Now, if I have this to be 90 degrees, I said, always make an angle with the horizontal. Anytime you make an angle with the horizontal, that what you are going to be using is that x is equals to what? X is equals to what? Towards the angle, Shebi? But in this case, anything you're going towards y is always what? Sin theta, Shebi? Now I'm telling you that this is when we have linear, vertical, and horizontal linear. But once you're not inclined at an angle, instead of it stressing to do this, if you are checking for the y component, consider y to be cos theta. It's not opposite. Then consider x now to be what?
Sin theta.
Yes. So, but I would like you to still go home, trying to think about all these things we've done here. You see that if you do it over and over, it will start to make sense to you. If you do it over, you see that it's not hard. It's just because you are meeting it for the first time. Alright. Alright, now see, if I know this, now let me find the top. So trying to find the top here, I'll have that this one is going to be. I want to redraw so that I can do it then. Go.
Okay.
I have WL, which is, I can say it's mg, that is mass and gravity weight, and that's what that's of the ladder. Then I have here WM, that is mass gravity weight of the man. Then I have this one, which is normal reaction of the wall. Normal reaction of the wall. I know you're pretty good. Then this one happens to be normal reaction of the ground. Okay. Now, if I'm doing this now, I'm going to be having this parallel to this. Now, somebody wants to ask me resolving this as well. Now, resolving this as well. Parallel to this. I just. So, if I do that, now there's an angle given to me here. Is it not true? You see, remember? Just look at that post and you see it. So if there's an angle given to me here, it simply means that I've gotten this to be the component. I've gotten this to be the weights acting on that ladder. Remember that this one is for this one. Weight, mass, and gravity of the man. So if I want to now get the angle here, this, I want to call this angle theta, but you can easily see that the reason why I have that angle to be theta is that if you look at this and look at this, let's say I put this force down, I've formed 90 degrees. Is it okay?
Yeah.
So if I have this and I've formed 90 degrees, remember that there is an angle on this thing this way. This one. Is it okay? Shebi?
Yeah.
And notice that this part is this part. Is it okay? Which means that I have 90 degrees this way. I have 90 degrees this way. So it's more like I have 90 degrees this way, and I have 90 degrees this way. So, which means, yes, looking at this now, if you check it, then I have so if you check it, yes, if you check it now, you can easily see that what this thing means is that if this is theta, let's say for example, I know that angles in a triangle is 90 degrees,
Yeah.
Now 90 minus anything, let's say I do 90, let's say I have here now for example, to be 60, so you understand this thing. If this is 60, the remaining angle here will what? 30, Shebi? 30 degrees. Now remember that from here to here, it's 90 degrees, is it not?
Yeah.
Now, 30 minus 90 is what?
50.
Which is the same angle here. Is it okay?
Yeah.
So instead of you stressing to do this thing, once you're inside the exam hall, always consider it that the same angle you have is the same angle here. If you let her succeed in this one, or that angle given must be the same angle. So no stressing yourself. So which means that the angle here is also theta. And remember I told you that if it's y-axis, use cos on the inclined plane, and if it's x-axis, use what?
Sine.
Yeah, very important. Now,
Right on.
if I have this, and please, even another way to think of it is that the angle made will always be with the ladder. That component. So there is theta here as well. There is theta here as well. So why I'm doing this thing is so that when you go home and you are reading, you have enough to read, enough to think about. And when you are through with thinking about it and reading and analyzing it, it will not start to make sense. Yes. That's where you see some people inside the exam hall. Some people will be writing exam inside the exam hall, people that don't used to read. They see one question, before you know something will activate them, you see inside hall, somebody say, Jesus! Because they'll just remember it like, he says, nah. Alright, so using these same concepts now, let's direct all our forces to this side now. So this one, remember this one, play this one our formula. So if we are directing now, please, I want us to be checking now. NW, since it's in x-axis, NW is going to be NW sine theta. Do you still remember I told you that you consider the x-axis to be sine and y-axis to be what? Now, that means that NW will be equal to this. Then for our NG, notice, this one now, notice, is in what? Y-axis, Shebi?
Yeah.
It's going to be NG cos theta.
Yeah.
But let's check something. Notice that if I put this thing now, just to be parallel to this. If I pull it now, that means I should be having theta somewhere here. Shebi? Now let's check. I already have NG here. Shebi? Then if I'm rotating opposites, there is opposite to parallel. Then this side becomes
One.
now 1.
How do you get one?
Yes, see. You remember that this thing I added here is to be my. I told you that we should see tall. We should see tall as y-axis now. Is it not true? When I added this thing, I'm adding this thing now, so that I am able to create the 90 degrees for the tall. So the minute I added it, I can call it y. That is why I said that man does it.
I don't. I'm hearing you.
You must see, I am here. Let's check something. If I happen to bring this in this way now, and it happens to be my ladder, the component, and I have a force on this way, or this way, it's the same as saying I come here and put this force. You see that there will be equal.
Yeah.
Now when I have this, it comes this way and this way. Then remember that there is an angle on this which is this way. Do you still remember?
I do.
So let's say I have my angle now on this to be theta. Is it not true? Yes. So if I have this, now, in the sense I have this. So, okay. Now let's check. If I'm carrying this thing now, if I want to carry this force now to this particular axis, hope you know that this force I'm seeing here is the same with this force. Are you aware?
Yes.
Okay, let's say I ignore this now. If I'm carrying this now to this, that is to horizontal axis so that I have 90 degrees. If I'm carrying this force now down, is it towards the angle away from the angle? Towards Shebi. And towards what? Cos Shebi. Shebi, you see that and it's a y-axis already. So instead of you stressing yourself to be doing all these things, just consider it that y-axis once it's inclined place will always be y-axis will always be Alright, so with that said, that means that my ng will also be equal to ng cos theta. I know I'm writing it out, so because when you are doing the talk of an object on an inclined plane, it's highly important to pay attention to the one in clockwise and anti-clockwise direction. Alright, now, this force, this one now, is in what?
It's in
vertical, should be y-axis as well. That means that I will have Wm, which is weight of the man, is going to be Wm cos theta. Is it not true? Yes, because it's a y. That means I will have Wn as well to be equal to Wl cos theta. Is that the whole force? Check for me. What about the friction? Notice the friction.
It is not. Yes.
This friction, Shebi, you are seeing it. We are not using it. Shebi, remember why we are not using it?
Why?
Even when we need NGs, because we are solving too much and we forgot ourselves. Do you still remember that this is our fulcrum?
It's fulcrum.
Shebi, Shebi, remember, and we are pointing on our forces to the fulcrum. Shebi, still remember?
Yes.
So, which means that when we are pointing on our forces to the fulcrum, we don't make use of that fulcrum. And notice that NG and F, frictional force, falls under that fulcrum.
Fulcrum.
Yeah, so let me just, I'll see you please see us. Alright, so please let me ignore that energy. So which means I'm just working with this force, and this force. I have no business with these two because they are degree volts. Is there anything like power volts? No. So you don't correct me again. See, if I'm not taking the clockwise stuff now, remember that we said that anti-clockwise, whenever you are rotating, is positive. Do you still remember? When we did circle, if today is your first time, notice that anti-clockwise direction means positive. While if you are moving in clockwise direction, it means negative. That's the rule. That's the rule. Somebody might want to ask me why is this so? Because if you check your quadrants, if this is 0, this part becomes 90. This part becomes 180. Is it not true? Notice that it's going in positivity. But the minute you start going this way, it means that you are now removing things and going back to 0. So that is why it's now. So if I know that, now let's check. This is our fulcrum, which means that we need to check the direction, the arrows now. If this is the fulcrum and we are directing all the forces, is this one going to be going, as it's going this way, is it clockwise or anti-clockwise?
It's clockwise.
Clockwise, which means that NW is this one, is going to have minus, because clockwise is minus. Remember we said that clockwise rotation means minus. We did it now. See, pay attention. Pay attention. I said when something is rotating in clockwise, I did not say your normal x and negative x axis or positive y and negative. I said if something is turning in anti-clockwise direction, it is going to be positive. Yes, because see, when you are doing 0 to 90, 90 to 180, 180 to 270, 270 to 360, notice that you are going in a clockwise direction. But when you are now doing from 360, removing your hand and going back to 0, are you seeing that you are going in clockwise direction? So for a circle or anything rotational motion, clockwise will represent it as negative, while anti-clockwise will represent it as positive. So with that said, since this one now, we've noticed that if you check it, this fulcrum is where everything is rotating to. Let all these ones constant. If I'm pointing this is very clockwise, so I go and put minus to show that it's anti-clockwise. Anti-clockwise. Now let's go again. This particular force, now notice something. This particular force, this one. If I'm going this way to this fulcrum from here, is it clockwise or anti-clockwise?
Clockwise. Anti-clockwise.
It is moving this way, Shebi?
Yeah.
Which means that just like your clock, it is moving in this order. Is it not true?
It is.
So let me come and put, that means that the two are in anti-clockwise, so positive, because the two are in anti-clockwise direction. Alright, so with that said, if this thing will confuse you, what is important, so that when you are pointing, you know the ones you are calculating together. So that means that I will now have that my clockwise course here is going to be NW sin theta. Is it not true?
No, minus.
Is it possible? No, when you are putting, hey Jesus. Sum of clockwise stuff. See, sum of clockwise stuff will be equals to 0. Is it not true? That sum of clockwise stuff will be equals to 0 is the same thing as saying clockwise torque and anti-clockwise, or you say sum of torque will be equals to 0. It's best put that way. Sum of torque will be equals to 0. That sum of torque will be equals to 0 is the same as saying that sum of clockwise torque will be equals to anti-clockwise torque. So which means that if this one will confuse you, I can write it the same as saying minus NW sine theta, then watch, plus WL cos theta plus WM cos theta. Are you seeing it?
Yes.
Now notice something. If this side is minus, watch, notice something. If this side is minus and this is clockwise, this one is anti-clockwise. Everything here, if I sum it up and I equal everything to the side, I'm removing this one because we are done with it. It's equals to 0. Let's say we want to cross a quality sign now. Let's say we leave the clockwise one side and anti-clockwise one side. You see that this thing will not become the same as saying minus NW sine theta is equals to, this one crosses over because minus, you see that?
Yes.
Minus WL cos theta minus, no, it's crossing over, minus
WM
cos theta. Now notice that by the time you do this minus, you are going to be having 2 of it, which will give room for minus and minus cancelling out.
Okay.
Yes, so that is why we say that once we are doing clockwise and anti-clockwise, what we just need to do is find the clockwise hole, put it in one side. Find the anti-clockwise hole, put it in one side. Finish. But if you want to do all this particular, maybe summing up everything to be equal to 0, you make sure that you don't miss the signs. Because if you miss the sign, it will affect your answer. So, which means that, I want to do this.
Rub it up.
Okay.
You don't understand this thing.
What's that? Well, it's not academic
Clockwise is positive, clockwise negative. When the quality crosses over, that one is
Results.
要放松紧。我们过的也做的很松。
So let's quickly round up. So that means that performance knowledge is equal to by end of sin theta is equal to WL cos theta. Just one. Give me the whole. That's all you have to market. Cos theta. But please write these formulas that when you go, you try to revise it. Tomorrow,
Thank you so much.
why is what? Why is end of scientific anti-clockwise? See now? See? Is it anti-clockwise or clockwise?
It's clockwise, clockwise.
Okay, sorry. Alright, so please, we can't say we stop here, sorry. I didn't see that. So please, tomorrow is another day. Tomorrow is Thursday, right?
Yes.
Tomorrow in the morning, we'll continue our class.
I'm sorry.
Serious lecture day. We'll definitely have class. Definitely have class.
What the fuck are we
In Jesus' name. In the name of the Father.